here because I can't advance it until I can see it.
We see it. At least I see it on my computer. So
Yeah,
get there.
it's going to take several seconds here.
Okay.
How's your cat doing?
How's the cat doing? Oh, she's great. She's very interested in this workshop.
We have samples that need a CAT scan.
Okay, it's starting to do something. Okay, great. So the point of this talk is to tell you about some first experiments we've done with space weathering on Ureilites. And as you can see here, we've got quite a big team working on this. And if we move on to the next slide, the first thing to talk about is why this is important. Fortunately, Dan introduced Ureilites a couple talks ago, so you've at least heard of them. Now, the motivation for this work is that dark asteroids have become objects of great interest these days, and in fact, the objects of quite a number of missions to asteroids, because they're thought to be primitive, volatile-rich materials. And this is based mainly on their spectral resemblance to carbonaceous chondrite meteorites. However, not all dark asteroids are primitive, and basically the reason we know this is because the Ureilites exist. So the Ureilites are a major group of achondrites. They're actually the second most abundant group of achondrites after the HED meteorites that are thought to come from Vesta. They're ultramafic meteorites that are thought to represent the residual mantle of some differentiated asteroid. And one of their most characteristic features is that they have very high carbon contents, where carbon contents are shown in this plot here for Ureilites compared to various other groups of meteorites. Ureilites have carbon contents up to about 8.5 weight%, with an average around 4.5 weight%, which is comparable to or higher than those in the most carbon-rich carbonaceous chondrites. So my first take-home is right here. It's simply that Ureilites represent an important reservoir of carbon in the solar system. They come from some reservoir, which, interestingly enough, is probably an inner solar system reservoir, despite the fact that they have carbon contents like the carbonaceous chondrites. So this is a plot that Mike just introduced to you, showing it's a very popular plot to show these days, showing that solar system materials seem to be divided in terms of nucleosynthetic isotopes into two distinct groups, well separated from one another, with the carbonaceous chondrites basically forming one group and non-carbonaceous chondrite materials forming the second group. And these are basically interpreted to represent outer solar system versus inner solar system materials. So what you can see here is that Ureilites fall into the inner solar system group, which is something that surprised everybody when it first became known because of their high carbon contents. And also they have oxygen isotopes, which are more like those of carbonaceous chondrites. But Ureilites seem to represent a reservoir of inner solar system materials, despite these high carbon contents, which makes them really especially interesting. So to talk about the reflection spectra of Ureilites, behind the motivation for this talk, what this plot shows is the visible near-infrared reflection spectra of what are called main group Ureilites, which are most Ureilites, typical Ureilites, which, as I pointed out, are mantle rocks. There's some spectral variation among them, which is mainly due to them having various ratios of olivine to pyroxene, various amounts of metal, sulfide, and graphite, and also having various degrees of shock. But you can see that at least some of them show Let's see here. Furthermore, urolitic samples from the Almahata-Sitta polymeteorite show even greater similarities to carbonaceous chondrites. Now, Almahata-Sitta fell in 2008 from the impact of asteroid 2008 TC3 in Sudan and is thought to represent urolitic regolith. So these samples, which are shown here in magenta, are urolitic samples from Almahata-Sitta, and they represent class in urolitic regolith. You can see that their spectra are much darker than those of the main group Ureilites, and some of them have strong spectral similarity to CM carbonaceous chondrites. They also show spectral similarities to some C-complex asteroids. And in fact, asteroid 2008 TC3 itself, which was measured in the 0.5 to 1 micron wavelength range, had a spectrum which matched most closely with F-type asteroids, which were a subtype of C asteroids in the Tholen taxonomy. So clearly some dark asteroids are urolitic rather than carbonaceous chondrite-like. And the important question is, how can we distinguish differentiated dark asteroids from primitive dark asteroids? This is certainly important if you're planning a mission to an asteroid and you have a specific idea about which type you'd like to go to. So one of the things that's essential to know to answer that question is how Ureilites react to space weathering. Space weathering of Ureilites had not previously been studied, and certainly based on space weathering studies of carbonaceous chondrites, you would expect some significant effects. So we started this work with 3 urolitic samples from Almahata-Sitta. The fact that they're at 2008 fall is important for this spectra because it means that they have experienced minimal terrestrial weathering. The 3 samples that we chose actually represent a range of Ureilite types, from the one on the left, which is very olivine-rich, low shock, and most closely represents an interior mantle sample from the Ureilite parent body, to the one on the far right, which is very fine-grained, highly shocked, and most likely, or comes closest to representing regolith from a urolitic asteroid. Now, the laser irradiation experiments were done by Jeff Gillis-Davis at the University of Hawaii. Each of the samples was powdered and sieved to less than 75 micron grain size. And micrometeorite bombardment, that component of space weathering, was simulated using pulse laser irradiation, which is a technique which Jeff and many others have described in quite a number of papers. And then reflectance spectra of each sample were measured after various intervals of laser irradiation. And the results are shown here, with the fresh samples shown on the left, and the results of progressive irradiation for each of the 3 samples shown on the right. Now you can see there's already variation amongst the fresh samples, with the most mantle-like sample showing the highest reflectance and a strong, very clear olivine absorption band, and the most regolith-like sample having the darkest spectrum and a much flatter spectrum with very little absorption features showing up. Comparing those to the most irradiated spectrum for each one, you can see that with increasing irradiation, all 3 samples became darker, redder, and showed decreased spectral contrast. And we also used Raman spectroscopy to look at what was happening to the graphite in the laser irradiation. The fresh spectrum of sample 38, which had the most highly crystalline graphite in the beginning, shows clearly the D and G bands of highly crystalline graphite. After irradiation, both carbon peaks broadened, the D band became as intense as the G band, and both of these are indicators of disordering of the carbon. I should point out that this was done by Mark Fries. In addition, we looked at high-resolution scanning electron microscope images of the irradiated samples, and in all cases, we saw significant melting or vaporization of the grain surfaces with production of nanophase iron and sulfide spherules. Okay, comparing the spectra for our three samples then with asteroid class means, this plot shows the 450 to 550 nanometer ratio versus the 750 to 550 nanometer ratio. And you can see the paths of increasing laser irradiation followed by the three samples in the three different colors. You can see all three of them getting increasingly redder, but interestingly, they're not all following the same path, and they're not all following smooth paths, which is something that we hope to look at in more detail. We can get even more information if we add albedo. So on the right is a plot of albedo versus the 750 to 550 nanometer ratio. Again, the mean asteroid classes with the albedo data being from Leinzer et al. 2011. Again, you can see all three samples getting increasingly redder and significantly darker in this plot. Now, one thing I did want to point out is these yellow stars, which actually represent spectra for other Alma Hadasida samples. And what's interesting is that all of these are actually darker and bluer than the three samples that we had available for this experiment. So there's an awful lot of variation within Alma Hadasida itself, which I remind you we think is a piece of Urcilite regolith. And we need to explore all of that variation in terms of what space weathering does to it. We can, however, certainly draw a general conclusion, which is that with increasing irradiation, all the samples seem to move away from C-complex asteroids and towards D, T, and some X types. We can also conclude that asteroid 2008 TC3 itself, which is shown by this orange thick line here, may not have been significantly space weathered, which is something which has been inferred by other workers from other lines of evidence. We can also look at the spectra of the fresh and the unweathered, the fresh and the weathered Ureilites in terms of the whole spectra compared to asteroid classes. These are now the 550 nanometer normalized reflecting spectra, so we're only comparing spectral shapes here. The first thing you can see is that there are no exact spectral matches with any asteroid class means for the fresh or the laser weathered Ureilites, but there's some interesting things that we can point out. For example, for both 22 and 38, you can see that the most laser irradiated, the most weathered samples are very red. They're red or redder than D-class asteroids, but they do still retain absorption features from their main silicates, which certainly don't show up in the D asteroids. And in fact, this is a spectral shape which is not showing up in any of the asteroid classes. In contrast, the sample which is most like what we think the bulk regolith was like is quite different. It was fairly flat and dark to begin with. It didn't get much redder, and all of these spectra, in fact, might be reasonable matches to some of the X classes of asteroids. On the other hand, it is still the case that all of these samples are actually classed from what we think represented regolith, and none of them individually represents the bulk properties of the Ureilite regolith. So, as I said, this is just an initial study. There's a lot of work to do, but our conclusions so far certainly show that space weathering probably results in significant changes in the reflectance spectra of Ureilites. So if we want to look for Ureilitic asteroids and we want to learn how to distinguish them from carbonaceous chondrite type asteroids, which are going to be a very different kind of rock, then we need to study space weathering of Ureilites. The results so far seem to suggest that non-space weathered Ureilitic regolith may resemble C-complex asteroids, whereas space-weathered Ureilitic material may resemble DT or some X-type asteroids, which certainly, if it holds up, would be of great significance to missions to asteroids, since we have missions currently going to C-complex asteroids, and we have missions currently going to D-type asteroids. as I said, there's a lot of work to be done because there's a lot of petrologic variation among Ureilite samples that needs to be examined still. We especially need to study some of the highly shocked Alma City Ureilites that most likely represent the bulk of asteroid 2008 TC3. In other words, what we think Ureilite regolith would be like. Thank you.
Thank you. I'll open this for questions. It's a great talk.
Thank you.
Okay, so Cyrena, I enjoyed your talk, but I got to ask you about this paper that came out last week. So the context of this for everybody is that, well, maybe I should, Cyrena, I could try to paraphrase, but you could probably say it better. Do you want to describe the paper that came out last week? And
No, go ahead.
Okay, so this group looked at a large diamond found, I think within a given Ureilite. They did measurements on it. They said it had to form under 20 gigapascals. And they said this diamond was also much larger than you would normally get from, let's say, some kind of impact event. And so they made an argument that this meant it had to come from a mantle of a body that was maybe at least, Moon to Mercury size. So it had to have been extracted from that. And so this was now in this Ureilite. So that's pretty provocative. On the other hand, there was a paper out just a few weeks ago talking about calcium isotopes, and they had this relationship that they thought went with planetary size, and they said the Ureilite parent body was more like 200 kilometers. So I'm confused as to the size of the Ureilite parent body.
Okay, just to comment on that calcium paper first, that 200 kilometers that was in that calcium isotope paper, they didn't derive that in that paper. They took that from one of my papers and fed that into their model. That's
right. You know, but it fit the trend.
Well, it fit the trend, but I don't know what that trend means. Let's get back to the paper that you asked about, which certainly was provocative and certainly was meant to be provocative and has certainly increased the size of the inbox on my email considerably. There was two lines of evidence that they used for the 20 gigapascals. For the main one that they talked about in that paper was not the diamonds themselves, but it was some inclusions that were in the diamonds. I won't go into detail describing it, but the mineralogic arguments based on those inclusions are very weak. They interpreted the composition of those inclusions as indicative of being a high-pressure phase, but there are other explanations. So I do not believe that inclusion evidence is strong at all. Secondly, the argument about the large size of the diamond is probably faulty. They took that work, the work on it being a large size from a previous paper. I don't know who the first author was, but Elgarezi was one of the significant authors of it. It was a diamond area in a sample of Alma City. So the sample comes from Alma City. And they interpreted it as being a single large diamond, which it was the largest diamond ever seen in, I don't know what, certainly in a Ureilite. I am working with a group of people who are doing micro Raman and micro XRD on a similarly sized diamond in a different sample of Alma City. And these diamond experts that I work with say that it's not a single large diamond at all. It's actually a cluster of microdiamonds, and they believe that they've got an argument that this is actually evidence of shock origin rather than a high-pressure static origin. It might be provocative, but in addition to all those arguments, which just come from this diamond occurrence, there's other strong arguments against the Ureilites coming from such a large body. If you had that high pressure, you would have other high pressure phases amongst the silicates, or you would have garnet or other kinds of minerals that just are not present in Ureilites.
Yeah, I'm nodding my head here because I wondered about that very thing. And it also just seems to me that, everything seems to suggest that the Ureilites experienced a large collision, and it's not clear to me if the collision's large enough, what kind of diamonds you should get out of that. I mean, we don't have a lot of experience with, let's say 100-kilometer or 200-kilometer bodies smashing into something that's many tens of kilometers in size. Who knows what that would yield? So, anyway, I was really fascinated to see what you thought about this paper, because if they're right, it's interesting, but I could easily believe it's not, their interpretation is not the only one.
Yeah. Are there questions about space weathering of the Ureilites?
I have a question on space weathering. This is Amanda. What is your interpretation of the process by which the Ureilites become redder upon space weathering?
Well, one of the main things that's probably going on is that the carbon is causing reduction of the silicates, the olivine in particular, and possibly pyroxene as well, and resulting in the silicates being basically peppered with very, very tiny grains of iron metal that are completely dispersed throughout the silicate material. And that's probably what's most responsible for the reddening and the darkening.
So a lot of like what happens on ordinary chondrites.
Yeah. I mean, on the other hand, that's a preliminary answer, and it's obviously, I guess, based on, experience, not my experience, but lots of people's experience with ordinary chondrites. As I said, this is a low budget proof of concept study that we've done so far, and so, for example, I haven't even had time to look carefully in the SEM at or do TEM work on exactly what happened mineralogically in those samples.
Okay, yeah, and I think Carly
we can do that.
Carly's wondering, if it's carbon or iron or what that the nanophase material is.
Well, I can't answer it because I don't know for certain, but I think it's more likely to be iron.
Cyrena, this is Kelly Miller. So you pointed out on your plots of the albedo versus the reddening, all those stars that were other class that hadn't been experimented on. So those are probably unweathered class, unspace weathered class.
Those are definitely unspace weathered class. The only space weathering experiments that have been done on Ureilites are these 3 that we did. Yeah, those stars come from published spectral data for other Alma-Hata City Ureilites, including some of my own work, but they have not been laser radiated.
Okay, cool, thanks.
So, Dan, any other questions?
Is Dan on?
I don't know.
Dan is on.
Next question. Dan is on. Would you like to lead a general discussion on all conversations and things related to this afternoon?
Sure.
Okay.